Great. Hello, my name is John Rula. As was said, I'm a graduate student at Northwestern under Professor Fabian Bustamante. And this was actually work done by a younger grad student, Dipendra Jha, who couldn't be here today. So I'm going to present this work on his behalf. And so the title of the paper is Exploring Xfinity, a first look at provider-enabled community networks. So similar to the previous presenter, we're also going to look at Comcast residential broadband performance, but in the past 2 years, they've actually been broadcasting public hotspots out of residential homes called Xfinity Wi-Fi. Okay, so if you take a close look at this picture, if you can, do you notice anything strange at all? No, you don't, because it's what you see everywhere. Everyone in public places in particular is glued to their phones, they're consuming content, and they're connecting through their mobile devices. So it's no surprise now that mobile devices are now the dominant form of content consumption for digital content. And so with this growing demand in content comes a growing expectation that you want connectivity everywhere and you want that connectivity to be high performance. Unfortunately, cellular networks are expensive. They have data caps. And in a lot of places, the performance isn't sufficient to do things like video streaming or for the needs of other digital content. So there's a promising alternative to this, and it's coming in the form of community networks, and in particular, these community Wi-Fi networks. So community networks have been around for around 20 years. They've been in research from things like all sorts of networking connections, like Ethernets to sneaker nets. And so it's the idea that it's a collection of networking technologies that are used for and by a particular community. And so more recently, these have taken the forms of community Wi-Fi networks. And so these are things like municipal Wi-Fi networks, or FON is another good example of that. And so recently, what we're taking a look at is this new class that we're calling provider-enabled community networks. And so they're called that because they leverage the existing deployments of existing customers. So in the case of Xfinity, each residential customer is actually in an opt-out situation where their home router is used as a public hotspot in addition to their own use. And so from this, they're able to kind of bootstrap their national deployment, getting basically free riding on their existing customers. And so what you see is it turns your home router into a public hotspot for both residential and commercial customers. So community networks face several common challenges, community Wi-Fi networks in particular. These are things like coverage. If I'm in a public place, are there wireless access points that I can connect to? Availability. If there are access points, can I actually connect to them? Can I actually use them? Are they usable? Performance, what kind of performance can I expect from these kind of Wi-Fi networks? And lastly, for deploying this, if I'm a participating host, what's the impact on my own internet connection? Are there going to be negative impacts that come from me hosting a public hotspot, either from FON or having a guest network or something like that? So in this paper, we took a look at the Xfinity Wi-Fi community network. And so right now, this is the largest provider-enabled community network in the US, possibly the world. And since deployment in early 2014, they now have over 10 million hotspots nationwide. And so, like I said before, this has been bootstrapped on their existing residential and commercial customers. And so there are a lot of news articles that came out when it happened, which a little bit of fear saying, what's this going to do to my network? Like, is this secure? And so, we think that this is actually a great case study for looking at these community Wi-Fi networks, because not only is there a large deployment, an existing base of hotspots, but it's centrally managed. Comcast or Xfinity is choosing which access points they choose to turn on or off. It has central access control. So we believe that this is a very good example and possibly like an upper bound on what these community Wi-Fi networks can actually achieve in the wild. So in order to measure this, the first thing we wanted to do was kind of characterize both the coverage, availability, and performance of this network that we see in two different areas. So the first is we wanted a dense urban deployment, and so we chose downtown Chicago. And then we also wanted a less dense suburban environment, which is Evanston, Illinois, which is a northern suburb of Chicago, which is actually where Northwestern is. And so we conducted 3 sets of kind of canvases in each of the areas. We, between September 2014, April 2015, and September 2015, so we collected 3 runs of measurements at about 2 apiece conducting them all in kind of the same methodical serpentine pattern through each of the areas. Now, because we wanted to mimic common use cases, we instrumented a mobile device, a Samsung Galaxy S4. So we wrote software on there that while walking around would continuously scan for Xfinity Wi-Fi APs. If found, it would kind of sort through them in the order of signal strength and would attempt to connect to them. If successfully connected, it would actually run a network diagnostic test on each of the access points. So, I mean, we're well aware that NDT underrepresents throughput, but in this case, we're actually trying to get a comparison between these environments. So we think that because it's consistent, it's okay. So first, let's take a look at coverage. So if we're looking at kind of geographic coverage, if I'm in an area, like how often am I going to see one of these Xfinity Wi-Fi access points? So we broke our grid from the previous slide into thousandths of a latitude and longitude degree, and we found that in Chicago, 70% of the grid was covered by Xfinity Wi-Fi, and that 90% of the suburban area was actually covered by these hotspots in September 2015. And so that is not really surprising considering that the suburban area is highly residential. Comcast Xfinity is one of the most popular and in many cases only choice you have for residential broadband, especially in Chicago. So we can see the differences there. We also looked at the growth because we had this kind of year of data during their initial deployment. And so we saw large growth both in suburban and urban environments. Suburban saw larger overall growth, almost doubling with 160 additional access points seen between Septembers of 2014 and 2015. However, on the urban side, we saw actually seven times the growth of access points as they were kind of, I guess they did their suburban deployments first and decided to focus on urban deployments slightly later. But one of the things to notice is on your far right corner is that the growth in 5 gigahertz is much greater than 2 gigahertz, and we're going to get into why in a little bit. Okay, so while this coverage is pretty impressive, the more important thing is, regardless of whether or not there's an access point present, can I actually use it? Can I actually connect to this? And unfortunately found that coverage in most cases doesn't actually equal availability. So we saw poor availability in both environments. In our urban environment, we're only able to connect to actually 15% of unique access points, similarly across 2, 4, and 5 gigahertz ranges. And in suburban, it was better, but still poor, connecting to less than 50% of access points attempted. So we did a little more investigation because we saw these numbers for approximately a year before. So in September 2015, we tried to investigate a little further and see what was going on and why these availability numbers were so low. And unsurprisingly, we saw that signal strength is one of the main culprits, that while these access points are present, most of the broadcast strengths of them are quite low. And so what we did is we binned access points by the maximum signal strength that we saw during each of our canvases, and we found that if your RSSI of your access point is between minus 70 and minus 80 dB, we're able to connect to only 20% of the access points. And if you have less than 80 dB, then you're connecting to 4%. It's basically, might as well be 0%. And you can contrast that to the higher signal strengths where we had almost 100% connectivity. But this also highlights one of the problems. So this graph is actually for connectivity to 5 gigahertz access points in Chicago. And we see that the vast majority are these low signal strength deployments. So even though we saw a lot of coverage in this, most of the access points we see are basically unusable. So again, we wanted to look at other features. So at that same time, we had an instrumented laptop with an Atheros chipset. So we were measuring wireless interference through channel busy time, which is the metric on the bottom. And so there's two things to kind of take away from this graph. One is the much greater interference that you have at the 2.4 level, as well as for each of the interference bands, even though they look similar, they both diverge fairly greatly above the 60th and 70th percentile. And we see that it actually ends up playing a pretty large part in performance as well as the aforementioned availability. So if we look at the NDT tests for these environments, we see that the suburban environments get much greater RTTs ranging from around differences between like 100 milliseconds in Evanston to around almost 500 milliseconds in Chicago. So we can see that like the much more challenging radio environments that urban environments present, because in downtown Chicago, it's mostly skyscrapers. There's actually L tracks that go through the streets. So you have large obstructions, a large amount of multipath effects, as well as like a greater density of businesses and residential and residences. And so we can see how that affects this kind of performance measurements. And similarly, when we look at throughput, there's almost a 10 megabits per second difference between urban and suburban on the 5 gigahertz range. So again, we see that these kind of challenging conditions of urban environments prop up again, and we see how that's negatively impacting performance. So overall, from our characterization, what we kind of found was that you can 5 gigahertz, the 5 gigahertz range, but there's less interference in areas with already lower interference can actually have much bigger gains. But ultimately, with these community networks, these community Wi-Fi networks, it's still an open challenge to how to deploy these things in dense urban environments in order to get highly available, high-performing connectivity. Okay, so the next thing we looked at was these hosting customers. So Xfinity basically opted everyone into this partnership of saying we're going to broadcast this public hotspot from your home router. It actually made it extremely difficult to turn off. You had to click through multiple screens on their website, and most of the time it was not responsive. So is there any impact from having this public hotspot? Is there any impact on the home router? So Comcast said no. They said that it's running on a separate channel on the cable modem and that there should be no interference whatsoever. So we actually went to test this, so we conducted a series of controlled measurements. So basically what we did was we had access to an Xfinity hotspot that had both a home router and was also broadcasting in an Xfinity Wi-Fi public hotspot. And so we connected with two devices. One was connected to the home router, the other was connected to the Xfinity hotspot. And we continuously measured network performance, again using NDT, while performing different levels of cross-traffic, both upstream and downstream, on the public hotspot. And upstream traffic was created through iPerf. Downstream traffic was created through a custom Python server that we had. And so first we wanted to look at the access link. We wanted to look at, we connected the home user over Ethernet to the router and conducted various levels of cross-traffic on the public hotspot. And we actually found that Comcast was being truthful. There was a separate channel between there, and that we saw basically zero variation between performance at any level of cross-traffic. So we believe them on that. However, when you look at the wireless, the problem is these hotspots, the public hotspots and the home routers are on the same radio. So one's basically a virtual WLAN that's running on top of that. So they're on the same channel. So anything you would get from radio interference from another user that's on the public hotspot is going to affect the home user. And we saw negative effects from this cross traffic with as little as 1 megabits per second of public hotspot cross traffic. And when we ratcheted that up to around 16 megabits per second, we saw a 67% decrease in home user performance. So again, while this is not necessarily an interference from the access link perspective, there is a huge impact on these hosting customers, especially for heavy traffic from the public hotspot. And again, if you look at the bottom's upload performance, because on the particular service tier we were using, the access link was actually the bottleneck on the upload performance, so we didn't see a lot of interference that way. And lastly, we're going to look at this other piece we found, which had to do with the intercompatibility between N and G. So if there happened to be a wireless G user that was connected to your public hotspot, we saw variations as much as 10 megabits per second difference between N and G users. So in the graph, the blues are cross-traffic that was generated from N devices. The red are performance measurements on the home user when there was cross-traffic generated on the G devices. And so both download and upload severely affected this performance on the home user. Okay, so in this work, we presented a first characterization of these provider-enabled community networks. We characterized some of the challenges that still remain in dense urban environments. And again, we discovered significant interference from public hotspot usage, both from large amounts of cross-traffic as well as from these interoperability between 802.11 versions. So since we ran the study, what's changed? So Comcast has said that they're now deploying dual band routers, which supposedly are broadcasting. If the home user is on 2.4, they're choosing the 5 gigahertz. And they're also deploying dedicated infrastructure in urban environments to try and alleviate some of the signal problems. But again, they're deploying these with new users at high service tiers, and they're trying to deploy dedicated infrastructure. So, it's not a solution yet. There's still a lot that remains to be done for them. And lastly, the things that we can say about kind of larger scale community networks. While this bootstrapping is great, especially in suburban environments where there's like a dense residential population and very relatively low signal interference, there are still problems that remain when doing community Wi-Fi in dense urban environments. So, thank you very much, and I'll take any questions.
Okay, we have time for a couple of questions.
Hi, very nice standing talk. Can you please go to slide 11? Yeah, so I was wondering, what does connect mean here? Is it just connecting to the access point, or are you actually transmitting data?
No, so this is just association.
This is just?
Association.
Yes.
So.
Okay. Yeah, because we did a similar study in Cambridge, and the results are very similar. You find that if you actually try to, even though you're associated, if you actually try to transmit or connect, if you use TCP to connect, then this will not also fail. So the 20% is probably not
a lot lower, right? That's a good point. Thank you.
Okay, Renata, there was another question before that, right? No? So Renata then.
It's more a question comment, because we have looked a little bit into this, because in France they had the free Wi-Fi, far Wi-Fi for a long time. And at the time, I find it funny because the way it happens in Europe is that in urban areas, we saw many more of these community access points. And the signal strength, like in our cases, because I guess the traditional partners are so small, that in our case, we actually got more issues like with higher signal strength and better quality. So I was just wondering, yeah, it would be nice to have a comparative study to see how these things would change from place to place. Because and definitely in our data, it looked very different from what
right.
we're seeing here.
So I would kind of expect that. So in downtown Chicago, we were in like the Loop area, which is heavily commercial. It's a lot of storefronts and like businesses that are in skyscrapers. So in terms of residential population, it's fairly low. So a lot of the access points that you get there are from Xfinity business customers at places like cafes and other things like that. So I'm not sure. In my mind, that's why the deployments were so low. But yeah, I think it really depends on the place.
Because in our case, they're being run from home networks. People are running their tests inside their homes, so it was already like apartment buildings and things like this, so that might explain it.
Right.
All right.
Thanks.
Well, let's thank the speaker again.